Okay, so here's what I was thinking about doing today. It's the last day of the quarter for us. We should make it a little bit casual. There's one piece of content that we haven't gotten to that we do in some previous years, and I always think it's kind of interesting for you all to know, given that you're always talking about, oh my God, we're out of memory bandwidth. I just wanted to talk a little bit about how memory works. So we'll talk a little bit about that. I'll do a really quick wrap up and things like that, and then we'll maybe open it into just a little bit of an AMA. We can talk. We can leave early. We can talk a little bit about, now that you've taken CS149, what might be some things that might be useful at Stanford to go do next. So that's the goal. Okay, so let's get into accessing memory, which has actually been a pretty abstract concept so far in the course, given its importance, right? So in your head, you're probably thinking about, okay, there's a processor, and then there's memory, which some of you might think of as DRAM, and I'll explain what that means in a second. And then to make memory faster, and by faster I mean reduce memory access time and increase memory bandwidth, we have this cache sitting in a modern computer. So if you think about this box here as the CPU or the core, you've got a processor core in there. For example, the Intel chips that you ran on have 4 cores in Myth. They had I'm forgetting now what they had on AWS. I think we gave you 8 core machines with 16 virtual, 2 hyperthreads per core. And then there's some caches, and on this diagram, I'm only drawing one of them. I'm drawing what's called the last level cache. So if you have an L1, L2, and L3, your L3 is your last level cache. Or if you just have an L1, well, your L1's the last level cache. We often like to think about the last level cache because that's the point in which memory requests that don't hit the cache now have to go out to memory. And then there's a box on any modern processor that's called the memory controller. And the memory controller is responsible for when the last level cache takes a cache miss, the processor has to go get the data from memory. And the memory controller is responsible for making that request out to memory and then grabbing the results when they come back and making sure the data gets into the appropriate cache and things like that. So that's what we're talking about. So where we're going to go is we're going to talk about the implementation of memory now as memory as DRAM. Okay. So if you got upset about the final and bashed your laptop over your knee and you opened it up and looked inside, you would actually see some DRAM chips in there. And one way you could think about a single DRAM chip is as an array, like a big array of memory cells. So every box on this diagram you can think about as holding a bit. And this is a memory cell, so we're actually working in the analog world at this point. And how do you think a bit is represented by an amount of charge stored in each of these cells? It's kind of like the inverse of a photo cell in your digital camera, right? Like you have an array of pixels, and light hits the photosensitive material and generates a voltage, and you have a capacitor to hold that voltage, which says this is how many photons hit the thing. Here's the opposite. We're trying to store information, so if we want to store a 1, we encode that as some voltage, and we want to store 0, we encode it as a different voltage. Okay. So you have all of these different bits, and they're organized on a DRAM chip actually in this 2D manner. Now down here at the bottom of the chip, there's 2 important structural pieces. First of all, you have your wires, your data pins, that actually connect this chip to the rest of the computer. So there's 8 data pins here, which means this DRAM chip at any one clock can only send 8 bits of information. There's a 1 or a 0 on each of these wires. Okay? And in order to access the DRAM chip doesn't actually send data from the DRAM array onto the wires. It actually has a buffer here, which is like a digital buffer, that stores the values, the bits, in one row of the DRAM chip. So this is called the row buffer. So this stores one row. And so when you access data from a DRAM chip, you're actually only accessing data for a bite-sized chunk of information stored in this row buffer. And I'll tell you, okay, so let's say that we have, we take a cache miss, and the cache, like the actual load instruction is, I need to access the address X. And at this point, we're talking about like the physical address X in memory. So the memory controller gets this command or this request from the processor. It says, hey, give me X. And really what that is give me the cache line that contains X. So when I say X, just think about X being like the start of a cache line. And every byte that the processor might access is going to be a contiguous part of some row in this DRAM array. So let's say we want to access the byte that I'm highlighting here in red. Okay, so the goal, what we need to do is we need to read the values out of those memory cells and then communicate those values back to the processor here over these bit lines. And so there's a number of steps to be able to do this, basically to convert this voltage, this charge stored in these capacitors into digital ones and zeros. So the first step in DRAM terminology is actually called pre-charge, which is kind of like getting ready to read a particular row. And in other words, what you can think about it as there's these bit lines, there's these wires that go all the way through the chip that are supposed to read off the voltage in those cells and communicate that voltage all in one from one row into the row buffer. So if this was software, I would say we need to make a copy of the data in one of these rows, put it in the row buffer so we can access the row buffer. But making that copy is actually communicating electrical voltage down these wires. So we have to set these wires to sort of a known amount. And that's like sort of this pre-charge. And that takes some time. And so on this slide, I'm saying it takes about 10 nanoseconds. So in memory, we think usually in terms of nanoseconds because we might be at a different clock rate in DRAM than the processor. So if we said clocks, it's a little confusing on what clock we're talking about. So, on the order of about 10 nanoseconds, this is like, okay, these wires are now kind of normalized to some known voltage. And if we drain the capacitance of some row onto these wires, their voltage is going to go up or down. Okay. So then we basically lock into the row that we want, and we row activate. And row activate is basically reading the charge from this row and bringing it down into that row buffer at the bottom of the chip. So that's the copy of information. And actually, it's interesting, since this is analog, that copy actually destroys the value in that row. So the only place where that row of information sits is actually down here at this point. So I had 10 nanoseconds to kind of get the communication lines ready. I had another 10 nanoseconds to sort of read off the voltage in that row, and now that information is sitting down here in the row buffer. And then given whatever particular byte that I want, then I can select that information. It's called column selection, because like the byte that you want is selecting certain columns in that row and transferring those bits onto the memory bus, and now they're moving back to the memory controller on the chip, and the chip's going to put them in the right cache, and so on and so on. So this process of reading a byte actually is like get ready, activate the appropriate row, then select the right column, and then move the contents from those 8 columns onto the wires. Yeah.
If we're reading like multiple adjacent bytes.
Great question. So what would happen if the next byte that you wanted to read was the next byte over in that row?
Well, we wouldn't be able to read it from the row.
You can't be able to read it from the row, and not only you can't, you don't really want to, because you have the whole row sitting right down there in the row buffer, and so you just move over. So if your first access was like needed a column access, a row activation, and then a column selection, your second access is actually faster because all you need to do is read off the next byte in the row, the data that's already in the row buffer. Okay, so this is kind of interesting, right? Like DRAM, so we've talked about accessing memory has variable access times depending on whether or not you hit the cache. If you miss the cache, DRAM has variable access times depending on the access pattern that you actually choose. DRAM may not be prepared or ready to deal with your request. It might need 20 extra nanoseconds to sort of get prepared, and that can be a big deal. There are a few questions. Yeah.
Yeah, on the previous slide. So when you transfer the column selection through the bus, does it still exist in the row?
Yeah. You can almost think about this as like we're basically digital at this point. and we're just sending those information out. And what has to happen is periodic, like if before we read the next row, let's say we want to read like this byte here. The first thing the DRAM has to do is actually write this data back to that row so we don't lose that information. So if we switch to a different row, there's actually an extra step. It's write back, then ready the data pins, then activate the new row. So it can actually be quite slow if you're moving around memory. Mm-hmm.
Is there any reason why the number of data pins isn't the same as the size of the cache?
Well, yes, and that's because you would love to have more pins, but this is expensive. That'd be like saying, why doesn't Highway 1 have 1,000 lanes? Because we would benefit from 1,000 lanes at rush hour, right? So we'll get back to that comment, though, in a second, right? And the other thing that you're saying is, well, why not more pins or something like that? This is actually the basic unit of DRAM. And so if you want a wider memory bus, you will use more of these. So DRAM's got to be cheap because it's kind of a commodity. And so the industry is standard on a basic DRAM chip with like pin width 8. And so if you want more of these, we're going to start stacking them, and we'll get to that in a second. So okay, so if everything, if you take away anything from that sequence, it's like DRAM latency is not fixed. All addresses are not the same. It depends on your access pattern how much you might get out of that. And that's a pretty big difference, right? Like, just think about it. I can either grab a byte every cycle, or I might have, and it takes about 10 nanoseconds to push that over the bus, or I could have like a whole 40 nanosecond, 30 nanosecond process to get the next byte. And all of a sudden, I've just cut my DRAM bandwidth by a factor of 3 or 4.
To what extent can we control that if there's the operating system sitting in the condition?
So what I'm talking about here is like saying when the computer, the processor, requests data at address X, it is the memory controller's implementation, it's that responsibility to map that to a place in that 2D array. You in software have very few mechanisms to address that. And there's some reasons why, which might be more apparent later. So the thing that you're noticing is that, let's say I have to make 4 memory accesses to these locations that I've highlighted in different colors. Like, let's say you're like walking through a linked list or something like that, or you don't know where that data is going to be at, where Malik put the data in the address space. Some of these, so I have just my operations are pre-charge, ready the bit lines, row access strobe, so RAS is select your row, and the column access, select your row and bring the data to the row buffer. And the column access strobe, the CAS, is the read the appropriate columns out of the row buffer. Okay, and so I'm highlighting the CAS in red because that's when the data moves over the memory bus, the memory pins. And if the memory pins are like the most precious resource in the system, your goal should be to make everything, you want to be able to use those pins at all times. If you're not making 100% utilization of them, you are wasting your scarcest resource in the system. So what are some things that we could do, given that this particular, what's the utilization of the memory bus in this example? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 4/10. Only 4 out of those 10 boxes are. So what are some standard tricks from this class in making better use out of something? So we could pipeline it. Now, how do we do that?
You would have to overlap the, yeah.
Okay. You're on the right track. There's a couple of different things you could say.
We increase buffer size.
And what do you mean? You actually mean increase the minimum request size, or something like
how you have that row buffer. You can have two rows. 2
row buffers. Okay, so basically you're kind of saying I want some multi-threading kind of ideas. yeah. So and you were kind of getting closer. Yeah, it's totally on the right. First of all, I want to just go with the easiest one first. Is you allow the chip to support bulk transfers. Like, you have actually a ability of, like, the command of the chip is not give me a byte, but the command to the chip is give me like 64 contiguous bytes. So the first thing in any computer system is you do bulk stuff if you want to amortize overhead, right? So that's one way to do it. And that's one way to do it if your access pattern affords big contiguous data. By the way, there's a reason why if you run right through your memory system, you get the best performance, and it's not just you're using the whole cache line. It's actually that the memory controller can communicate with the DRAM system in the most efficient way possible if it knows the access pattern is all contiguous. That's also the reason why there are cache lines. Cache lines are 64 bytes, which helps suggest, like big bulk contiguous granularity transfers are more efficient, right? Like a memory bus is 64 bits on modern Intel stuff. A modern cache line is 64 bytes, 8 times larger, which means there's a lot of bulk transfer there. Now, what you all were hitting at are really good ideas, and that's exactly what's going to happen. So basically what's going on here is this is your classic problem of I have an operation with some latency. I need to hide that latency. And in this class, if you want kind of arbitrary latency hiding, you multi-thread. And if you want kind of more structured latency hiding, you pipeline, right? You put more operations in flight. And we're definitely going to pipeline this thing. So here's what we're going to do is every DRAM chip has like one of these arrays, and it has a row buffer. And the way they do their pipeline is they're going to take all of this, and they're going to replicate it. So here's what's going to happen is we're going to share the data pins. Remember, like multi-threading was like sharing the processor and having different outstanding requests. Here, the outstanding requests are into the array. We're going to share the data pins, but we're going to build more row buffers and more. We're going to share the row buffer and the data pins, and we're going to build more DRAM arrays. Okay, so we're going to have what in DRAM terminology are different banks. So what's going on here is while we are waiting for for rows to activate on one bank, we're going to make a request and start reading the data from other banks and sending data over the bus from other banks. So notice here that if your addresses are interleaved over the banks, I can start the processing for bank 0 or be moving the data for bank 0 when I'm initiating the row access on bank 1. This is your classic pipelining example, like you said. So every DRAM chip, if you go buy a DRAM chip, it's going to have some number of data pins, which is basically going to be 8. It's going to have a row buffer to store a row from any of these DRAM arrays. And there'll be multiple DRAM arrays, which are called banks. That's packaged up. And then if you want a 64-bit bus, this is an 8-bit bus, then you start stacking them wide. So this is, like when you go on Amazon or Newegg, you buy yourself a DRAM DIMM. So the DIMM is, IMM is the inline memory module. There's just 8 of these DRAM chips sitting there. So this is now a 64-bit memory bus. 1, 2, 3, 4, 5, 6, 7, 8. So your Intel processor, your standard processor connected to a 64-bit memory bus, the memory controller is sending a command, and that command is not, I want address X, but that command is, I want the byte at bank B, row R, column, whatever. And all 8 DRAM chips get that same command. They all return their data in bank B, row R, column 0. And that altogether is 8 bytes of data. So it's the memory controller's responsibility to say, oh, if I'm supposed to get a 64-byte cache line at this address, where in this 3D address space of bank rows and columns is that data? And you issue the request. People looking confused? Yeah.
Sorry, in the previous slide, when we're replicating the banks...
We're not replicating. We are. There's no data replicated. There's just simply, in this case, 3 banks.
Yeah. Sorry. But it seems like the column accesses happen immediately one after another, and there's no pre between them.
Here's the pre. So if I'm accessing bank 0, here's the pre on 0, here's the grabbing the row into the row buffer, and then there's the read the data out of the row buffer for an access to bank 0. While we are reading the data out of the row buffer on bank 0, we're pre-charging bank 1. Okay, got it. So the vertical data lines are replicated. The replicated lines, there are n different DRAM arrays, and they all hold different data. Yeah.
How smart is it to like if you have a contiguous array, would it try to scatter these across so you can?
Well, let's think about it a little bit. So let's think about reading one cache line from this thing, right? So one cache line is 64 bytes or 512 bits. Okay. So imagine that I do the most simple thing, which is I put, because like the width of these DRAM arrays is like 2,000 bytes. So maybe I put the whole cache line in a contiguous row of one DRAM chip. How long does it take me to read an entire cache line? So my first byte comes from this DRAM chip. My second byte comes from that DRAM chip. My third byte comes from that DRAM chip, and so on and so on. So even though I had a 64-bit memory bus, I'm only using 8 bytes. So what does this suggest the answer needs to be? I have to, yeah, I mean, like one thing is I should interleave the address space over my DRAM chips. So that notice now when I say read bank B row R column 0, the same address, or not the same address, the same like location in all of the chips, I get what happens to be 8 consecutive bytes in the physical address space. Now, of course, if I wanted 64 bytes for the cache line, I would need to do this 8 times in time. Yeah.
Slides ago, when you have the multiple banks, is that you have multiple banks, but then it's one row and one set of data pins?
Yeah.
When you go one slide forward, it looks here when you do each of these little modules that it's kind of one bank, and each of those is its own row.
Oh, what I want you to think of, sorry, yeah, this diagram here, every one of these boxes is a DRAM chip. And every DRAM chip inside of it has multiple banks, which I did not illustrate here on the slide anymore. Sorry about that. Yeah, I probably should have done that. But you could just think about it. A DRAM chip is a module which accepts as input a request, which says, give me the byte in bank B, row R, starting at column 0. Right? And so now keep in mind that if I do this, let's do this. Let's go here. Okay, so let's say I stride my bytes across the DRAM chips. Does it make sense that we're going to get 8 consecutive bytes here? Right, okay. So, but we have a whole cache line, right? We need the next 8 bytes. So I would probably put the next byte, interleave it amongst the DRAM chips, but put it in a different bank on those DRAM chips, because I want to initiate that row access to the next byte immediately in the next cycle.
So when the...
Yeah, I should change that diagram to show that there's a couple of banks under each of these, yeah.
So does the memory controller, when it makes that request, does each DRAM module know to start recharging the next bank?
No, it'll look like this. It'll look like there will be a the DRAM. Okay, so think about it this way: in every clock, the memory controller is sending this command. So let's say it starts getting started on that command immediately, just for simplicity. In the next clock, it'll start pre-charging bank B+1 or something like that, right? Because the next command will say, I want the data at bank B+1, right? So the memory controller is going to give the memory system requests in a manner that, based on its knowledge of how memory works, it can satisfy those requests as quickly as possible. Yeah, it's pipelining the request straight in. Mm-hmm. And if it's a whole cache line, let's say it's 64 bytes, that request actually could be burst mode transfer, I want 8 bytes located starting at B, R, and column 0, right? Because what I would probably do is I'd put the next bank, if those are the bytes I'm reading there, well, the next byte I read from every DRAM chip will actually be in the same, I'm in the wrong place, in the same row. So in this case, I would not start a new bank transfer. I would just say, look, I need 8 consecutive bytes from the same row of all DRAM chips times 8 DRAM chips. That's going to get me to my 64. Yep, exactly.
Do the requests from the memory controller also also go across the same data pins?
No, there's usually like a command bus also, yeah. Yeah, there's usually like a 64-bit data bus, and then there's a command bus. I haven't ever implemented one of these myself. I'm not sure if there's any clever temporal multiplexing of the pins, but I'm pretty sure that there would not be, because in modern DDR, you're actually doing transfers twice on the rising edge and the closing edge of the clock. So unless you're really creative, I don't see how you could squeeze any more information down there. But yeah, okay. So this is like your basic memory unit. And then sometimes you'll hear things like dual channel memory system or something like that. And so like you can think about this as one channel between the memory controller and a memory module, a DIMM. And notice that like one channel has one command per clock or something like that. And the same command is given to everybody. A dual channel memory system is just to take this and make another one. Right, so here's an example of I got ahead of myself. So one more thing before we talk about dual channel is, remember we have the processor down here, and the processor is just generating cache misses, and cache misses turn into I need this cache line, and those are requests to the memory controller. And the memory controller takes all these requests for cache lines and translates those into memory channel requests, which is like, I need this bank, this byte, this row. Right? So the memory controller is mapping physical linear addresses to spots in a DRAM array. Now the memory controller is getting just kind of random cache misses, whatever the algorithm does. And what any modern memory controller does is it just starts enqueuing those and buffers them up, and then reorders all of those cache misses such that if it can find requests that it needs to make to the same bank, to the same row, it will reorder the requests in order to maximize this sort of hit rate. So it's going to basically reorder all the processor's memory requests in order to try and get the highest bank pipelining and the highest row buffer locality. Because remember, the processor's memory requests might be coming from all the different applications on the system. So you might have an application that's reading linearly through memory. There could be another application that's linearly reading through memory running on a different core. And think about how those two memory request streams are going to interact. All of a sudden, you thought you laid out your data perfectly, but now it's like core 0's over here, core 1's over here. Now you're going to thrash that memory DRAM chip. Yeah.
So how many requests are we going to wait for when we're kind of reordering these requests again?
This is an implementation detail, right? So you have, on one hand, buffering will increase latency. On the other hand, buffering and reordering could increase bandwidth. So if you're bandwidth bound, you want to buffer aggressively and maximize bandwidth. If your application is latency sensitive, like some real-time thing, you might not be so happy with a heavily buffering memory controller. An NVIDIA memory controller is probably the most complicated part of the chip and could be buffering tens of thousands of memory requests, actually. Because everything is bandwidth bound on the GPU. So it's just like, I'm going to wait and see if there's any more requests for this open row for the next 10 nanoseconds. And if anything else comes in, I'm going to let them go to the front of the queue because they're going to be really cheap.
You just mentioned the latency versus bandwidth bound. Does the memory controller dynamically determine that? Or if you build one memory controller, it will be kind of...
That is your discretion as the implementer of a memory controller thing. Right? So what's happened is that all the sophistication of an out-of-order, complex superscalar processor, we kind of stopped getting more sophisticated there. We even built cheaper or simpler processors for a while there. A modern GPU probably doesn't do nearly as much smart stuff in the core than even still a modern CPU does. What's happened, and so we started building all of these cores. But all of those cores share a memory system. And so all of that scheduling logic that we used to have to schedule instructions has turned into papers and algorithms and other stuff to figure out, how do I take a look at my cache miss stream as it's coming in and guess whether this is latency bound or not latency bound, and how do I come up with a good scheduling policy? So in the late, in the from like 2012 to 2015 or 16, computer architecture was all over this, right? Whereas like in the 90s or early 2000s, they were all over how to build a branch predictor for an instruction stream. So they took the complexity out of the processor and basically shoved it in the memory controller, which is getting requests from like 16 cores or like 32 hyperthreads, and is trying to figure out how to reorder all of these requests from different processes to maximize pin utilization of the DRAM bus. Or energy. The other thing is like you're actually trying to maximize energy too, so, or minimize energy. Right? Okay, so the last piece of this is take what we just did, and if we want more bandwidth, we're going to start replicating. So if you hear dual channel DDR4 memory system, that's just that 64-bit bus connected to a DIMM. There's just two of those connected to two DIMMs. And now when you have two channels, you could actually say, maybe this channel is actually sending different commands to this DIMM than that other DIMM. But everything connected in a channel is the same command. So here's an example of something, like something you might see on a website like DDR. So DDR4, that's a memory technology. The number after it's actually just the clock rate of the memory bus. And so all of these things are 64-bit memory buses these days. And the 2400 is a kind of, bigger numbers sound better in computing. It's really a 1.2 gigahertz memory bus. So it's sending data, or like the cycle is 1.2 gigahertz. And it turns out that the first D is the DDR is actually is double data rate of memory technology. It actually sends 2 transactions per clock on the rising edge and the falling edge of the clock. So if you multiply 1.2 by 2, you get 2400 memory transactions per second over a 64-bit bus. So if you say 64 bits times 2 times 1.2, you actually get 19.2 gigabytes per second, right? And if it's dual channel, you just multiply everything by 2, and you go look up at the specs of the memory system. You'll say something like, oh, the memory system can do 38 gigabytes per second of bandwidth, and that's where that number comes from. So this is like a very standard thing in like a modest PC or something like that. And then it says like at the time when I looked this up, it was about a 13 nanoseconds CAS. So that's how long it takes to get data that's already in the row buffer out of the DRAM chips over the out onto the bus. Yeah.
I've seen that they always care about the CAS over your row calculation and all that. Is that just because you might want to stack it so really it's just your serious?
Yeah, you got to think about that because if you've got a nice friendly memory access pattern, it's how quickly can you get that data out. Yeah. Mm-hmm. Mm-hmm. Yep. Okay. And that's non-trivial, right? Because if you think about a modern processor running at 3 gigahertz, at 1 gigahertz, that's what? That's a nanosecond, right? Did I do that right? Yeah. Yeah. And then, so if you're running at 3 gigahertz, it's 0.3 nanoseconds. And so you're taking 30x that just to get the column out of the row. That's non-trivial. Now, of course, your memory access time is going to be all the cycles needed to get from the processor to miss a couple of caches and get off chip. So there's a lot more latency in there than just accessing the DRAM itself. But that's just how it adds up. Yeah.
I'm just wondering, how does the memory system have a fault tolerance?
Oh, so one thing I did not talk about here is any kind of fault tolerance, meaning like if a bit flips or something like that. Typically, what happens is you have these error correcting codes, and so if you buy slightly more expensive memory or server memory, largely, instead of a DIMM with 8 chips in it, there'll be a 9th chip, and the 9th chip is the redundancy. So basically, you can check to see if you have, depending on how you do things, like you can actually check to see if you at least detect if there's an error. So you just actually burn a little bit more capacity for that. Okay, so I think the takeaway would be that's a little bit on how DRAM works. And the big conclusion is there's a significant amount of complexity in the memory controller scheduler to take requests from the processor and reorder them such that those requests hit the DRAM in a very, very friendly order. you can think about it like, you did like with your flash attention, right? Like you're reordering the computation so it hits the cache. This is about reordering the cache misses so they hit the DRAM in a nice way. And obviously this is being done by hardware, not by the programmer. Okay, that's all I wanted to say on that. Just kind of cool, just so if you ever get asked in an interview, how would you schedule a DRAM request stream? That's pretty cool. All right, so now the problem, of course, is that we are bandwidth bound all the time. And so one way to, so you can think about it as like DRAM sits over here, on the board, and then there's those pins, and those pins go over the entire board to the processor over here. Now, the problem is like the only reason why we have 8 pins is that those are really expensive. To your question earlier, so there's a lot of interest in bringing that processor a lot closer to the memory, so that the distance information travels is less, which makes it economical to build a lot more pins. Okay, and the number one way you're seeing this like today in high performance things is via a combination of chip stacking and co-locating the memory on the same die, silicon die, as the processor. So here's a diagram of kind of how, like, if you went and got like a server class GPU today, that you might hear about this HBM, high bandwidth memory, or HBC, hybrid memory cube. I think HBM has basically won the competition. So you get a lot of HBM these days. So here's how it works. Here's my GPU or CPU over here, and typically that GPU or CPU is plugged into a board, motherboard. And then there are traces, almost copper traces over that motherboard to a DRAM chip that I plug into the motherboard. These days, if you want this high bandwidth memory, this is your CPU or GPU, and it's right on a silicon chip. Right? It's on a silicon chip. And on that same silicon chip is a memory module right into it. So now the connections between these two are actually wires on a piece of silicon. They're not board traces. Okay, and then the DRAM chip is actually stacked, which means that these DRAM chips are on top of each other physically. So, and the key technology was this thing called the TS via, through silicon via. So you can think about the wires that used to be like 8 wires at the edge of the chip are now wires that leave the chip throughout the DRAM array. So you kind of get area amount of space and not one edge of the chip amount of space. So you can run a lot more wires right off the bottom of the chip, like from everywhere in that array. And those wires have to run through the DRAM chips below it. So there's these vertical wires that then go right on the, right into a piece of silicon right over to the GPU. So if you bought one of these things, this is all in the same package. What I mean by that is like it'll look like one chip. So that's allowed people to put a lot more wires out of the memory system to the CPU. And I'm talking about not 64 bits anymore, but 1,024 bits. And so if you go buy a modern Intel, a high-end like supercomputing Intel thing, or an AMD or NVIDIA GPU, this is now the chip. This is the the processor. This is what's called the silicon interposer, which is a piece of silicon, and that processor's on the silicon. And then there's 4 different stacked DRAMs next to it, all of which are 1,024 bits into the chip. So this is a 4,000-bit memory bus. This is fast. This is now delivering 720 gigabytes per second of bandwidth into the chip, and that was back in 2016. Now we're significantly higher. I think we're closer to like 2 terabytes. Right, but this is a fixed amount of memory. So this is 16 gigabytes of memory only back in 2016. Now we're higher. And if you want large amounts of memory, then you have a traditional memory bus that goes out to DDR5 or DDR4, and you might have hundreds of gigabytes or terabytes of that. So this is a form of DRAM that is not the cache. There might be like an 80 megabyte L3 cache here. If you miss the 80 megabyte L3, you have access to, in this case, 16 gigabytes of about a terabyte per second of stacked DRAM. And if you don't fit in the stacked DRAM, then you got to put your data out in conventional memory, and now you're back to 300 or 400 megabytes per second, or gigabytes per second. So the memory hierarchies are getting really, really deep. And flash attention, thing you guys implemented was initially designed to fit the intermediate matrix in the 16 gigabytes of HBM, right? Instead of going out to DRAM on these chips. Yes.
Is the latency like?
It's lower also. It's also low,
yeah.
Higher bandwidth, lower latency. Now in a GPU, we don't care as much about that latency because we can hide it with multi-threading.
Right.
Yeah. Or pipelining. But yes, lower latency, higher bandwidth, lower energy. Okay, so like, if last day of class, if you walk away with anything, it's really that, and a lot of times parallelization is pretty easy. It's really trying to figure out how to get data to your damn processors that's hard. It's scheduling that's hard. And so you've been doing it yourself in this class. Flash attention, your CUDA programming assignment was very much about locality. And then the hardware folks are designing better memory systems for you. And the general design principles are like, look, either data needs to be located next to the processor, or the processor has to be brought closer to the data. And one thing that we haven't talked about very much in this class is if you're bandwidth bound, it almost always pays off to data compress. Because if you're bandwidth bound, your CPU is idle, or your GPU is idle. So actually have it burn more instructions to move less data. So like GPUs, for example, for texture data and other stuff, actually, when you take a cache miss, it compresses the data before putting it out in memory, so it actually moves less data. And then when you want the data back, it actually moves the compressed data onto the chip and then decompresses it into the full cache line. It's a very common thing to do in graphics. All right, so that was a little bit on memory these days. Anybody worked on any of this stuff, actually, like an NVIDIA internship or Apple internship or anything like that? No? It's Apple, you probably couldn't say, so. Okay, I think we're basically done. We're basically done. So let me wrap up some technical stuff here. Is a few takeaways for the foreseeable future. I mean, if you look at Apple Silicon these days, or what's in your iPhone or Android phone, it is a heterogeneous multi-core processor with multiple CPU cores, multiple GPU cores, neural cores, cores specific for processing the data in your sleep schedule and stuff like that. The only way things are going to get more efficient going forward until there is some massive breakthrough in technology, on the level of like being more optical or being more quantum or something like that. But for the foreseeable future, it's going to be it's already happened through parallelization. It's going to be through specialization of certain sorts. And so there's huge interest in making these specialized processors easier to program. The other thing that I really hope people walk away from here is most software is shockingly inefficient compared to what modern computers can actually do. Like we saw in assignment 1 that a well-written C program is 40 times slower on our laptops than an extremely well-written program that uses the vector units and uses the SIMD. And specialized processing is another 10 to 100x on that. So just when you're working in labs and doing future work, if someone says, okay, we're about to scale up to a big cluster, sometimes that's the right idea because it can be hard to optimize your program. But sometimes it's like, gosh, we could either work really hard to scale up to a big cluster or wait overnight or something like that, or we can put a little bit of effort in and run 1,000 times faster. Sometimes that can be absolutely game-changing for folks, or it might allow something that nobody thought was possible on mobile to become possible in mobile. The fun thing about this class, at least, is that almost all computing applications these days are actually the types of applications that fit into the mold of what we talk about in this class. We don't have to go to big-scale scientific computing to be applicable. You take an interview at Apple to work on mobile team right now, efficient software and power efficiency is what they care about. You go to Waymo, that's what they're going to care about. And so there's just a lot of places that one could go from this class, even more so with all these large AI-based language models that are extremely efficiency-bound right now. We've talked about a few themes, like we've talked about identifying parallelism, which I say often is kind of the easiest thing for everybody to do. What's much harder is scheduling that parallelism once you know the dependencies. And we've talked about that in the small and the large. And then we've also talked a lot about how to make our lives easier by relying on higher level abstractions, which in future courses, if you're programming in TensorFlow or PyTorch or programming in SQL or something like that, you can think about, oh my gosh, like think about all the parallelization and efficiency that's going on under the hood that you don't have to think about because someone's put in place a useful abstraction. And we've talked a little bit about how hardware works, so that at the very least, if somebody comes up to you and says this computation's taking 3 hours, you can kind of call a little bullshit on them. You're like, if I think about it, this thing should only take 5 seconds. You must be doing something really, really wrong with how you're scheduling it. You'd be surprised how much that happens. Okay, let's see. So just some practical things, next steps. We do teach other courses. So Kunle has his hardware programming class next quarter, I believe. So if you're interested in using spatial, and I think they teach in spatial, if I remember correctly, that could be interesting. There's, as some of you know, there's 229S, the new course that's simultaneous with this one, which maybe we should think about putting those on different quarters in the future, because it feels like you should take 149 and then you'll get a ton out of 229. But there's that's a great course. I've been tracking that new course. So that's really cool. In the spring, I teach graphics next quarter. So if you're interested in graphics, by all means, join us. But if you're not interested in graphics, I teach this hybrid graphics. And, like basically, if you take 149 and you take vision and graphics, and you put them together, 348K in the spring is that. It's a small course. We typically keep it around 30 people. We read papers on how to build systems. Systems like video processing at Google or Halide, or these days like how to serve ChatGPT in the data center or something like that. So we read like very, very recent papers, and we discuss them, and then it's a project-based course. So the idea is how to think about building these visual computing systems where the goal is to produce or understand pixels. Yeah, and then of course there's like a lot of the standard fare, like EE280 is a great course if you want to get into more hardware, operating systems here. There's so many courses in the department that start touching on parallelism in different ways. Okay, so then there's the idea of research, right? And after taking 149 with the assignments that we give you, which are not the easiest, like many of you through this course have really started to build up some real programming chops. Like you know the fundamentals, and so you now kind of stand to, if you're interested, maybe kind of fitting in a little bit in one of the research labs in a systems group, like Kunle and I's, or any of the other systems faculty. And I do encourage people to think about that, not because I'm really advocating for research. There's folks that work with us all the time, and they're like, I do not want to be an academic or a researcher. But they want to treat an independent study just like a class. They'll take 3 units or 4 units, and their role is to jump in on an existing research project and often perform more of a software engineering or support role, saying, hey, we were thinking about parallelizing this, but we don't have anybody to do it. Would you want to see if you can make this 100 times faster? And if so, we can put you on a paper and you can be part of writing a paper or something like that. I think one of the coolest things about being at Stanford is, and compared to other places, you could probably take a pretty good parallel programming class at many universities across the world. It really is the peer group at Stanford that's so interesting, right? Working with your partner or working with other people in the class or the CAs, that's what's really interesting around here. And so if you can believe that your master's students or undergrads that you're working with now, you're like, wow, those folks are really cool folks. I like working with them. Our PhD students are not too shabby either. And so, it can really open your mind up and whoa, that person's only 2-3 years older than me and they are awesome. Maybe I should be, I can get to that level too. So, it can be kind of fun if you find the right fit. So let me just tell you about one project in my lab just to be more concrete about things. So as many of you have probably experienced, people are very interested in training AI agents, whether they are robotics or just software agents these days, to do things in the real world. And I come from, I'm interested in graphics. And so for me, I'm like, oh, you guys are doing all this stuff in these simulators. Well, there's not, what is a game engine is a simulator? And so a lot of this work, here's some example. You might have heard of like the OpenAI Dota playing bots, along kind of old news now. Here's another example where like there was this 2-on-2 game of hide and seek where two of the agents had to hide and the other two agents had to find them. There's a lot of stuff in robotics and stuff. Well, the problem is that in general, people were basically taking Unity or Unreal and running a simulation in them. And if you don't know anything about this modern AI stuff, it's that, well, there's kind of two things you can do. Is you can have an LLM tell you what to do, which sometimes works. And then the other thing that sometimes works is you could just have large amounts of trial and error. Robot, try and do this task. Oops, you fell on your face. Okay, take that as an error and make a small correction and try again. And because of all this trial and error, people are using pretty massive resources to learn these skills. Like clusters of GPUs, billions of time steps of trial. And it was like computing all these time steps in like these 3D environments was taking all this time, and as a result, they were just loading up on big clusters. And so one of my students kind of saw all this and said, well, the reason why they're doing that is they're running like 10,000 copies of Unity all on a different server, playing the same game. Like one server per and he's like, or you like run like 30 copies of Unity on the same box, and that's like, they start thrashing and all. Like, this is a bad way to do this if your goal is to like play out 10,000 games. So he started going like, okay, what if we just design like a mini game engine from scratch? And the goal of the game engine was not to render pictures for humans, but was to carry out 10,000 independent copies of a game, but do so kind of in a lockstep so we can get all the good coherence and all the good properties of parallelism. So, here's an example of a game that was created in his system. So you can just kind of see some of the requirements. This is that hide and seek thing. We should have there's two teams. Like there's these two guys, I think, or maybe, I think there's these two guys and those two guys. And you see that they've learned to like win the game by like pulling. It's like a small child. Like you pull something in front of your face, and technically by the rules of the game they can't be seen, and so they win. Right. So I'll play that again. So they have to learn how to like hide. Other people, like in this case, like they have to learn to go, see someone else. I think that's what the guy walking to the right is. But some interesting things happen. This is some work originally done by OpenAI, and we just replicated it. So there's a lot of pretty gnarly computations. Like you've got to do physics. You've got to simulate the physical world. By the rules of this game, or even just to give people a sense of the environment, you actually have to do a bunch of ray tracing. Because you have to say who can see who. And then there are just rules like gameplay logic, like when I get close to this block and like press the button, it should attach to me because I picked it up or something like that. So there's arbitrary logic. So you want to be able to write your game logic like, okay, like here's an event handler, here's some basic script to say when I'm close to this thing and I pick it up, it's who owns it property turns into me and stuff like that. So you write your game in your normal way, but we have ways of basically like, think about like ISPC-ify it or CUDA-ifying it across everything. And we actually run the simulation like this. So you don't think parallel, but we parallelize it. And now we line up tens of thousands of games at once. And just by this kind of basic CS149 kind of thinking, we can go quite fast. So this was on the order of speed-ups over off-the-shelf open source things on the order of 2 to 3 orders of magnitude. So stuff that used to take like 64 GPU clusters for a week can now be done on a single GPU in an hour or two. Or someone training this overcooked AI thing, which is a common reinforcement thing, it used to be about 4 hours for a training run that turned into 3 seconds. Because these are pretty simple games. So that's like an example, right? And it's pretty easy on a project like this to be like, oh yeah, we'd love to have someone add a feature to the game engine. So we had an undergraduate who's a good undergraduate, has taken my 348 class as like a freshman or something like that. He's the one that actually just built a brand new rendering system that amortizes over 10,000 different scenes and builds the rendering system. So now like we can render these things. So if we don't render pixels, we can run this thing at like 2 million frames per second. But now we're actually rendering pixels in case you wanted to train an agent that actually took images to actions. We can do that around 200,000 frames per second. So for small images and stuff like that. So that's a pretty big difference. 200,000 frames per second. Okay, let's drop it to 100,000 because you got to run like a deep network or something too. So about half and half simulation. So it's like 100,000 frames per second. In 10 seconds, you have 1 million examples of experience. Right? Like so, you're into 1 billion examples. You're getting close to 1 billion examples in a weekend. So maybe that'll allow some stuff. So there's ways to it'd be really great to be able to write the scripts in Python and have the Python compile to CUDA PTX stuff so that you can write your scripts in Python instead of CUDA right now. There's a whole bunch of little projects that would be extremely technical that people could help out with. So that's an example of a project where if folks are really good implementers, it's really easy to get you involved. Other projects are harder to get involved. We have one master's student that took 149 last year, and he just wanted to start implementing Minecraft in this thing. So he's implementing his own Minecraft that runs at 600,000 frames per second. So the hypothesis here is just now that you are kind of midway or 3/4 of the way through Stanford career, it's probably a good time to start thinking about what the heck you actually want to do when you get out of here. And this is the point at which sometimes starting to do some of your own projects or some less directed stuff can be a heck of a lot more useful to you if you're disciplined about it than just taking the next course and figuring out what some professor comes up with 5 assignments. You're like, okay, I don't want to think about what to do. I'm just going to do what they're told. Right? So that's just something I like to tell people roughly around this time in their careers. What's the conventional path at Stanford? And let's be honest, it's the conventional path at every other top university, which is you guys all got really good AP scores. Probably took more AP classes than other people. And there's this notion that if you get A's in a whole bunch of CS classes, you're sort of doing a good job, right? So you get that 4.0 GPA. You can go to the job fair. You can hang out in a tent with some free food. Some people give you some callbacks, and you're going to get a good job. You're definitely going to get that first round interview. You're going to get a good job. Wherever the good jobs are these days. I don't know where the hot place is these days, but it used to be if you could get your Facebook or Meta, or at the time Facebook, if you get your Facebook, Google, and Dropbox offers in your senior year, play them against each other, and then you're done. Just go there for 2 years or something like that. Nowadays, I'm not sure if it's so obvious where the so-called default job offer is coming from. I'm actually curious. Is there a singular set of 3 or 4 companies that everybody's trying to pursue? I don't get the sense that that's true anymore, actually. Yeah.
It's just completely oversaturated. That doesn't really work.
Yeah, I don't think it works anymore, actually. Yeah, but it used to be that case is. But the thing that does work a lot better, and I'm using my name on this slide. I'm not saying come work with me or anything like that. But every year there's a few folks that come up and say, hey, this course I took with you, whether it be one of these things, was pretty cool. Is there anything else I can do, right? And sometimes I say, hey, I remember your assignment 3, you did every extra credit in the book. Yeah, sure. You seem like you know what you're doing. And then I'm oh, well, we definitely are looking for someone to hack some hardcore CUDA code right now, or be able to implement a new application and benchmark the hell out of it because we want to compare that benchmark to something that we're doing in the lab. That's basically how people start to get involved. You just kind of are useful in some way. And sometimes, not all the time, I would say about 50% of the time, maybe 30% of the time, it really is the right student to get involved with my PhD students, and they basically just start acting like a PhD student for independent study credit or something like that. And we get to know them, and they have a really good time, and they start doing something a hell of a lot harder than anything I could reasonably ask you to do in a class, right? Because if I asked everybody in the class to do some of the things that my PhD students do, that would be a tough class. And typically what happens is, there's a whole bunch of letters of recommendation and all this phooey. But typically what happens is that student gets around to the senior year, and at some point, I don't know, I'm bored. I'm hey, by the way, what are you doing, right? Next year or something like that. And they're I don't know, I've got these offers from these companies, but I'm not so excited about them. Or they're I'm just really want to get into this part of the industry. And sometimes I know people. Right? And what I mean by that is it's not I'm calling in favors. it's like one of the more interesting aspects of the job is to get students that are great where they want to be. So it's a good thing for me to go, oh, like the students like in my class, and they've been like in the lab for like the last 6 months, so I know them pretty well. That's when I go call my friend up and like, oh, they want to go into the game industry, and like, I don't know, like Roblox is offering them this like entry-level driver position or something like that. That's a total waste. That's when I go call the like, you know, lead engineer at Roblox and say, there's like a superstar here at Stanford that wants to work for you. Like, can you get him a good job? Right? And so that's the stuff that opens up doors. It's not like you got to know people because they like, if you know someone, you'll get a good job. It's more like, you know, Stanford professors are pretty well connected with other people in the industry that are doing interesting stuff because they used to be our students, or we're hanging out with them and stuff like that. And everybody in the world loves to pass on really strong people to other people and make stuff happen. And so that's a really great part of my job. I love that a lot more than like, you know, dealing with people that have to take a remote exam next week. You know, that's like the last thing I want to do. And that's where you find the pretty interesting stuff, right? Like I'll give you an example. There was a student quite a while ago now, like 5 years from now, came up to me in my equivalent of CS348K. It was like, I'm really interested in PhD programs in graphics, and actually at the time like photography, like Google photography stuff. And this student was good, but I was like, you don't have a chance of getting into like, you're going to want to go to a good PhD program. And I was like, let's just be honest, you haven't done the research, you don't have the background to get into the type of places that you want to get. I was like, I know you're good enough, but you just don't have there's no way it can be justified in the admissions process. And so I was like, well, what do you want to do? He's like, I want to do like really awesome, like fancy Google camera app kind of stuff. And I said, oh, okay. So here's what we're going to do is we're going to so Google had just published the paper on how their HDR and portrait mode stuff works, right? And I said, okay, in my class, because this is an open-ended class project, here's what I want you to do. I want you to read the paper, and I want you to try and implement the paper. That's your class project. And if you can get this thing implemented and get it to work, that's like the perfect opening for me to go tell the person who I know that runs that group that you're looking to like get in with his PhD students and do some work, right? Because this was a person that was like second half of senior year. There was no opportunity for them to do research or build a resume anymore. And the folks like saw that class project and they were like, yeah, if he's taking like Kayvon's classes and Kayvon says this person's good, and this person has put their actions on like reading our work and implementing their own version, we think this person's hireable, even though most people we hire are PhD students. And so they struck a deal. They said, look, we'll have you work with all of our PhD hires as long as you promise if we're going to put the time into you, you need to stay for 2 years or something like that, right? And so he said, okay, fine. Like there's no better way for me to prepare to grad school than go work with the top people in the field in Google at the time. And that's how it worked out. He worked with them. By the second year, they had given this person some opportunity to write a paper or two. And then he had the strongest resume in the planet and got into Berkeley 2 years later, was already halfway done, got out of Berkeley, I think, in like 4 years. And I think now he's at Anthropic or something like that and doing stuff. So that's just an example of like, if you get to know your faculty a little bit better, we want to help, right? So that's just some advice. Again, not for me, maybe for anybody here at Stanford. You might like other classes better, but usually you're here because the people around here are pretty good. So use that resource. So just a few practical things about that. Here's what happens almost all the time. So I get students all the time say, I'm really interested in parallel systems. Is there anything I can do in your lab? Which at first I was like, great, that's awesome. And then I start wondering, my next question to myself in my head is, can I find a good fit for the student? And a lot of the students come up to me and say this before taking 149 or any of these classes. And for those students, I kind of have to say, look, we have to assume you have some base knowledge. We can't teach you the assignments in 149 in an independent study. You might as well just take the course. So typically what the faculty look like is like, well, is the student really interested, or do they just kind of think that they're interested? And if they're really interested, they would have taken your course, and they would have done a really good job on at least something in the course to show that they're really interested in it, right? Like if somebody comes up to me and says, I have a B in 149, I'm like, well, if you were really interested, like I gave you like some of the coolest stuff that I can think of, like why didn't that get you excited? And sometimes they're like, well, I had this other thing, but if you look carefully, my last 2 projects are awesome. I'm like, oh yeah, that's true. Like let's go forward. So there's a little bit of that, right? So there is a filter of, there are plenty of opportunities in class to show that you're super interested, especially in classes with projects. So I kind of ask my questions like this. Have they taken the courses that are relevant to doing anything in that area? Are there examples of them just going beyond expectations? Like this person's actually interested. Have they been talking to me in office hours? Have they worked on anything of sort in related classes? Or do they have like an industry internship at NVIDIA? I'm like, oh, you've been on like the CUDA team at NVIDIA? Like you totally know what you're talking about or something like that. Okay, so there's also a few pitfalls after I say all this stuff. So first of all, I often get a lot of emails right during finals week. And like everybody else, like our heads are kind of going all over the place during finals week. And sometimes like after we get all the grades done, that's like right when I'm about to head off to family. And I just don't get around to responding until I get back. And at that point, that email is like 1,000 emails down in my inbox, right? So if I don't respond, just please keep emailing again and email again loudly. Like you would, it sounds very uppity, but there is a point for your Stanford faculty where it is no longer possible to actually answer the emails that we get with a personal level. And so if we don't respond, it's not because we're not interested in you. It's just slip through the cracks and just be persistent. So email again in all caps in a friendly way with a smiley face to make it, right? Or plant your set outside my door and say, hey, at some point today you're going to be free. I'm just going to stand outside and wait till you're free. The other thing is that we want you to have a good experience. And sometimes it's hard to find a good fit. You know, there are projects where we're just getting started. We don't really know what we're doing. And so it's hard to give somebody something to do if it's like 3 days later we were like, oh, just kidding, we thought that was a good idea, now we're going this direction. So sometimes I'm just going to say, like, look, you're awesome, but like I just don't know how to fit you into anything right now. And so that will happen as well. So that, you know, don't take that personally from any faculty that gets you. So I think that the big point here is now that we get later in the junior, senior, master's programs, your job is to try and start making some decisions about where do you really want to get yourself. Make some bets. And sometimes those bets are best done outside the classroom. Sometimes they're not done outside the classroom. And so I just want to make sure that people aren't overfitting to some stuff that you might hear, which is like, look, like you have to have this internship, you have to have this many A's or something like that in order to get those good jobs. That's how you get like the hard to get normal jobs, I think, actually. But there are definitely grades that you can figuratively get from working with folks through a recommendation or through, you know, just some professor going, hey, have you ever thought about this company? Because like you might be really interested in going there. There's ways to do things that are maybe a little bit better than A's and A+. So I'll leave it at that. We have 5 minutes. I guess I can hang out a little bit. Have a good break. Send me a postcard or something if you're going somewhere interested. I'll put it on my bulletin board. All right, let's get out of here.